Yeah, I'm Robert Böhm, head of the part-time scientist, and today I will tell you why the moon is the next big thing and why you should think about getting back there. So, first of all, I will show you a very short video about what we want to do. Oh, it's already playing.
Our closest neighbor in the solar system, and yet it has always seemed distant and unreachable until now. Now, a private team of engineers is working to change that forever. They come from different backgrounds, countries, and fields of expertise. But what unites them is true pioneering spirit and the will to try the impossible. Who are these guys? They are the part-time scientists, and they are full-time crazy. Audi engineers are supporting them to build and test the Audi Lunar Quattro to make it ready for the moon's challenges in the context of the Google Lunar X Prize. Together, we will take collaboration and teamwork further and reach for the stars. Wherever this mission may take us, together we are following the true meaning of Vorsprung durch Technik. Join the part-time scientists on their mission, the mission to the moon.
So that's just a very short way to introduce on what we do. So just to sum it up, we want to send 2 rovers to the moon in less than 2 years from now, all of this as a private entity. So who are we and why are we doing this? Let me explain a bit. So we're a team of scientists and engineers which came together in about 2008, inspired by the Google Lunar X Prize Challenge. The Google Lunar X Prize Challenge is basically a bet by the 2 founders of Google who said, the first private individuals who send something to the moon after 40 years, after Apollo, will get $30 million from us. So I saw this bet when they offered they sent out the press release to everybody, and I was really amazed by the idea and even bringing up the question on why are they actually doing this? You know, why is such a big company offering money for private people to think about getting back to the moon? The reason, what I realized, is that they're doing this because we currently have an issue. Yes, there currently is no way that if you're sitting here in the audience and you have the greatest idea for a space startup, you have the greatest idea to do something in space that could, for example, make our life here on Earth better, then there's no way that you can find an investor for it. There's no way that you can prove your business model, because right now everything in space is really restricted, inaccessible, and hard to prove that you have a business case. And that's what they try to incentivize to change. So there are many teams in the world, that science teams, who tried to work forward this competition, and we are now amongst the 5 top entities doing this. And as of today, which is something I'm really proud of, is that we're called the part-time scientists because we started out doing all this in our free time. It was a relatively small investment in the beginning, but now we managed to become so-called full-time scientists. The name no longer holds to space, so that's why we call it PT scientists today. And we still have like 11 people working full-time and 35 people contributing to this project as part-time scientists. So to give you an idea, what does it mean when I call somebody a part-time scientist? That's, for example, somebody like Jack Crenshaw. Jack Crenshaw is the trajectory calculations lead for the Apollo program. He did the trajectories to get Neil Armstrong to the moon and back safely for an Apollo mission 11 to 15. And he's now working on our team to do the trajectories for our mission. So he's long retired, but it's really good to include people with such a heritage of knowledge into his mission today. So, and basically, what we are as an entity is that something that you probably noticed from the video before is that we managed to get Audi as a technology partner and sponsor for this mission, so that we're working together with them to getting this technology done and get it ready for the environment of the moon. Also, we're working with a number of other entities like the German Space Center, the DLR, and the technical universities. Yeah, and also something which is a little bit newer is the cooperation with NASA Ames. So let's talk about the moon. So why should you actually think about going back to the moon? What you can see here, that's the landscape of Apollo 17. The moon itself is something that is really not something where you would like to make a holiday trip. There's totally no reason to go there. You have like a temperature shift of 300 degrees Celsius. We're talking about minus 120 degrees to plus 160 degrees almost instantly in temperature shifts. You have about 500 times the radiation than you have here on Earth. You have no atmosphere. there's absolutely no good reason to go there. So, but actually all of these things which make the moon such a harsh environment and make it complex to get a robot there and even send humans there, make it absolutely perfect to do exploration and look for resources, look for the things that we can use to go back in space. So Apollo 17 has something really unique about it. It's located in the Taurus Literary Valley, and that's actually where we want to touch down. We want to touch down a little bit 5 kilometers outside of the initial landing zone of Apollo 17, so in this large valley. And the special thing about Apollo 17 is that they have this little guy parked quite outside of their landing zone. That's the Apollo LRV. That's the Lunar Roving Vehicle. It's one of these things that NASA built specifically for the Apollo program to make the astronauts more mobile on the surface, and they did it really fast. They developed this entire unit in less than 6 months, which basically meant that they didn't do it like they did the normal Apollo missions, so they used a lot of components which were actually not meant to be used this way, which is really good for today. Because if you look at it, if you go back to the Apollo 17 landing site and visit this little guy, what we will want to do, so we want to have one rover, drive over to Apollo and analyze the remains, or however, how big or small they are. It could be a pile of dust, or it could be the entire structure still standing, and analyze the remains of all of these components to see how this material evolved over the years. So it has been on the surface of the moon for over 42 years. So that's the primary mission objective that we have. That's the main reason why we want to go there, is we want to understand, in terms of material science, how this material works on the moon. So if you have to get this knowledge, then you can actually decide what materials to use, what worked for 42 years, and you can then decide what materials you need for a lunar base or for ongoing robotic exploration. So that's the primary goal that we have. A secondary goal that we want to do is so-called in situ resource utilization. It's a very complex term, which basically means that we want to bring a number of experiments to the moon which show that you can use the resources on the surface of the moon right there. So something that people don't know so much about the moon is that it actually yields a number of resources that you wouldn't expect. What things that you can find on the moon is, for example, like water. And from this water you can actually derive oxygen, and something that you can also derive is hydrogen. So, and this is something pretty surprising. You wouldn't expect this from this gray and dusty area, that you can actually get water, oxygen, and hydrogen. What does this mean? You have everything that you need for humans to live there, and you have everything you need to get rocket fuel. So, and if you now think again what I said about the moon being such an unfriendly environment with no atmosphere, with just 1/6 of gravity, it actually becomes the perfect stepping stone for reaching out into space. Because sending a rocket up there here from Earth is something extremely complicated and cost-intensive. It's cost really into the multiple millions of dollars. So that means that if you can derive all of these resources on the surface of the moon, then you can actually build your spacecraft right there and launch it from the surface. There's no air resistance, and there's nothing keeping you except this 1/6 of gravity. That's something that you want to keep in mind. So that's the reason why I think that the moon is our stepping stone into space. So that's what the landing area looks like. That's the parking position of the LRV. And so how do we actually get to the moon? What's basically the idea of our mission? So we want to launch towards the moon in the third quarter of 2017, and we were utilizing a commercial satellite carrier. So that's actually a rocket that's not intended to get something to the moon. So if you're doing private space exploration, you have to be really flexible and explore new ways. So something that we want to do is want to use this rocket, which has a relatively small amount of payload, and it's not getting to the right kind of orbits to get something to the moon, and put something that we call a so-called landing module into the tip of it, which gets us all the way to the moon. So that's what a landing module looks like. So that's the capped transport. In Apollo, we had multiple terms for like the transfer phase and the landing phase. This is just one module doing everything from getting in from sub-GTO all the way to the surface of the moon, which is a really complex thing. So what you need to do, what this vehicle needs to do, is to do autonomous landing and navigation. So it needs to get to the right orbit, and it needs to autonomously get down to the surface and find a safe landing spot, which is really, really complicated because there is no pilot on board. You have no Neil Armstrong sitting inside the capsule who can decide, okay, this landing site looks good, this is a little bit complicated, there's a crater there. So you have to do all in real time and make the decisions on board. You cannot rely on ground control because the moon is about 400,000 kilometers away. That's actually not far in terms of space, but it's far in terms of communication. You have a signal delay of about 3 seconds. So, and 3 seconds might not sound as much, but this spacecraft is traveling with about a little over 10 point something kilometers per second. So, and if you think about this unit, then 3 seconds delay becomes a huge issue for you. So, there it is. Okay. So, and what we have is what we have on board of the landing module. We have the mobile exploration unit, as we call it. So that's something that we've been working on since the beginning. So what we've proven is that we have a concept which is just based on a 4-wheeled vehicle. Because normally in space, if you think about all the rovers that you ever saw, you will only have seen like 6 to 8 wheels rovers. But we managed to prove that with a 4-wheel configuration, it's a fully electric system, of course, which is movable in all directions from the topside view, that you can actually go to all of the areas and you can get around all of the important obstacles. So that's, for example, what it looks like if you qualify such a unit in a solar radiation chamber. That's when you try to find out, for example, what the vast amount of solar energy that you get on the surface of the moon does to your hardware in the terms of thermal. It's black. Oh, perfect. But it's not the slide that I want to show. Ah, there it is. Okay, so that's the flight unit that we're currently assembling. So that will be the final version of the as the rover will look like. There's also a previous prototype, and it's black again. There's also the previous prototype where we won an award from Google for the development of it outside of this hall that you can see there. So and yeah, that's what the final version will look like. And I don't know. Could I get another slide? Yeah, perfect. So what's so important about getting back to the moon? The important thing about the mission that we want to do there are the so-called payloads. Payloads is what you need, what in aerospace, what you call technology that you take to the moon. Normally people pay for this. In our case, we have some payload customers as well, but we have some experiments which we developed on our own, which we'll also be taking to the moon. So first of all, things that we take to the moon, that's what is written in the uptime caller. That's, for example, a very special camera, which is very similar to the one that the Mars rover has, the MSL, that's currently driving around Mars. So it's possible with this camera to analyze things and materials just by looking at it, taking multi-layered pictures of it. And so that's very, very important so that you can do non-destructive analysis of heritage hardware, for example, like the LRV. Or that you can actually understand the resource surface composition for resources just by looking at it. So, and the second thing, which is something, it has a really complex name, it's a Lunar Soil Additive Manufacturing Unit, is basically what you would call a 3D printer. So what we want to try to do is actually send a very small unit to the moon, deployed on a lunar surface, which is capable of collecting lunar dust, which is called the lunar regolith. That's a very fine powder. Refine it and divide it by its parts so that we can get out a certain component with a defined melting temperature, and then do something which is called laser melting, and try to produce the very first man-made, in this case there's no man, but let's say robotic-made part on the surface of the moon, you know, ever being done just using the resources there. That's the important thing here. The only thing that we use is the soil of the moon and the energy that comes from the sun. So that's a huge thing for space exploration, because right now all the costs in space are defined by getting something into space. You have to get your fuel into space, you have to get your spacecraft into space, you have to get all the resources that you need for your mission, water, oxygen, as I mentioned. But you have all these resources on the surface of the moon. The lunar regolith has high amounts of titanium, aluminum, and other compounds, so that is really, really interesting as the building blocks. So there are two things that I want to show you. That's the camera that I mentioned, and that's basically what you can see in the middle. That's the unit that you could use to analyze samples of the surface. The other two things, that's the reason why they look like human eyes a little bit, are the stereo cameras that you use for the robotic stereoscopic vision, so that you can understand in 3D what your environment looks like. And something that I want to show you a little bit more in detail is this experiment, which is something that we're doing in cooperation with NASA. That's the so-called Lunar Plant Growth Experiment. And if you read the name, then you already knew what it's about. It's not about growing potatoes on the moon, but it's actually about growing a small seed of plant on the surface of the moon and trying to understand how plant growth works in this gravity environment. Because right now, something that most of you are not so aware of is that plants are not growing normally in space. So if you're watching the plant growth experiment on the ISS, you will notice that the plants, as scientists call it, are confused. And they're confused, and nobody really knows why. There's some theories, of course. The theory is that they're confused due to the lack of gravity, or that they're confused due to the lighting, the missing lighting environment. But there's no defined answer, and it's really close to impossible to figure it out here on Earth. So the idea is to deploy this small set of experiment on the surface of the moon and watch these plants grow for about 2 days and see if they grow normally. And that's the good thing about this experiment, is that it's developed to be an open experiment, which means that school classes can get a free set of it and can actually replicate the experiment as it's happening live on the moon. So and that's something hugely important for me personally, because this could actually inspire kids to become engineers, and actually get involved into space exploration. It might be much better than if we get more lawyers, for example. So I'm totally in for space engineers, and we could definitely lead more of them. So and that's the reason why I think this experiment is important. Yeah, that's about it. So if you want to learn more about the mission and what we do and follow our progress, just visit missiontothemoon.com. And yeah, if you have any questions on why it makes sense to go back to the moon, feel free to ask them.